All right, welcome to Essay 2 of Exam 1 on Bio 461. In this discussion, I'm going to discuss RMP of a cell or resting membrane potential of a cell and how it is developed and how we reach a certain magnitude that represents the resting membrane potential through concentration of ions. I'm going to talk about action potentials and how we reach a graded potential versus an action potential, specifically in a neuron. And then lastly, I'm going to talk about capacitance of a neuron and link constant and how it is related to myelin and why signals would travel faster in a myelin sheath. Now to begin, what exactly is resting membrane potential of a neuron specifically? I will explain that in a moment. So say we have a cell. Let me redraw that. Say we have a cell, and when we think about what is inside and outside the cell, we would think of all these different ions that contribute to the extracellular and intracellular fluid. For example, we know that sodium has a very high concentration in the extracellular fluid. Likewise, we also know that potassium has a high concentration inside the cell. We also know that many other ions, such as calcium and chloride, contribute to what's called the resting membrane potential, and we know that each has a certain concentration inside and outside the cell. And we can represent that by drawing these different volumes. And so what does this have to do with resting membrane potential? Well, the cell, by definition, has something called an electrochemical gradient. And I can demonstrate that with a tank, and say in that tank we have a semi-permeable membrane, and with that membrane we have positive charges and negative charges on both sides. In the last video, I talked about in osmosis how things want to typically move from a high concentration to a low concentration. That is also the case with ions. So potassium will want to flow in that direction because it has a lower concentration on this side than on the left side. And we call that our chemical gradient. However, because these ions are charged, they are going to be repelled by all those positive charges going from the left to the right side. And so eventually they will want to go in the other direction where the negative charges that never crossed are. And we call that the electrical gradient. These two forces together both happen in a cell, and that's what we call the electrochemical gradient. Now there's three things that contribute mostly to our resting membrane potential and how the electrochemical gradient is established. The first thing would be the sodium potassium ATPase pump. Now in the last video, I talked about how the sodium potassium pump basically acts as a carrier protein that plays a role in primary active transport. So basically, as a review, we know that sodium, or 3 sodiums, will go outside the cell against its concentration gradient, and 2 potassiums will flow into the cell against its concentration gradient, and that is by the help of ATP. Now, what does this have to do with the resting membrane potential? Well, by definition, the resting membrane potential is about negative 70 millivolts, which basically describes the charge of the cell based on the concentration of the ions flowing into and out of the cell, which I'll explain later. So here we got 3 sodiums flowing out, 2 potassiums flowing in. Well, just because we've got sodium and potassium flowing in 2 directions does not mean one area is going to become more positive and the other is going to become less positive. These ions also travel with chloride because it needs to stay neutral. And when it travels with chloride, we see that because we're losing more net negative charge than gaining it, the cell is going to be a lot less negative than it initially was, which I failed to mention earlier. We have this, by definition, the inside of the cell is going to be more negative and the outside is going to be more positive. And this is one reason why the cell will be more negative, is because we are having a net loss of -1 negative charge, which is why the cell becomes less negative. Now, another thing that contributes to the resting membrane potential is called the potassium leak channels. Now, when a cell is at rest, meaning ions are not really flowing into or out of the cell at such a rate that it impacts it significantly, we have what's called potassium leak channels. And basically, those leak channels are always open, and that high concentration of potassium is flowing out into a low concentration out of the cell. And these are always open, and so that is why potassium has the highest control over every ion. So none of these other ions essentially have leak channels, and if any, they have very, very little at resting membrane potential. So sodium, by definition, has the strongest influence on the cell, which is one reason why it is -70, which I will get to in a moment. And then the last and final thing that contributes to the resting membrane potential is negatively charged proteins, which we know would be established by negatively charged amino acids that accumulate into the negatively charged proteins that are very prominent inside the cell. And that's what contributes to our negative charge of -70 in the cell. Now, why is the cell -70, you ask? Because we have what's called Nernst potential, and each ion has its own unique specific Nernst potential, and I can explain that through an equation known as the Nernst equation. And all that is we can represent that as -61.5 over Z, which represents the charge of the ion, times the log of the concentration of one specific ion inside the cell over the concentration of the ion out of the cell. And like I said, this only contributes to one specific ion. So it will only talk about potassium. It's not talking about every single ion in or out of the cell. It's talking about one specific ion. And so now we have what's called driving force, which essentially is the resting membrane potential, which in this case would be -70, minus the Nernst potential. And this is how we can calculate the driving force of the ions going into or out of the cell. And so let me further describe driving force to you as if we were in a physics class. Say I had a cell that had a strong influence to get out, but also was influenced to go back in. However, that's represented by a smaller vector, meaning an arrow that is constituting a magnitude and a direction. Well, we know the net force, represented by this third arrow, is what's called the driving force of the cell. So if the cell ion has a stronger vector going out of the cell, it's going to have a driving force that's stronger going out of the cell. Now, by definition, we have ions. We have our ions, potassium, sodium, and chloride, that each have their unique driving forces. So potassium has a driving force of plus 55 millivolts. Potassium, by definition, has negative 94 millivolts, and chloride has around between negative 60 and negative 80 millivolts. Now, because, like I said, potassium has the strongest control of what the cell will be because of its leak channels, that is why it is at negative 70, because the driving force is at negative 94. Chloride also has a pretty strong driving force, but it stays inside the cell. So that is another ion that strongly contributes to the driving force of the cell. Another thing I want to mention is when we think of driving force, by definition, what I did was I created a table to remember we've got our driving force, if it was positive or negative, and this is off of the calculated driving force, and whether or not we have a cation or an anion. So if you're wondering, if we calculated the driving force of sodium, for example, we would have negative 70 minus 55, which would give us negative 125 millivolts. When the driving force is negative and you're working with a cation, it will want to flow into the cell. However, say we had potassium, we have our driving force of negative 70 minus negative 94. Two negatives make a positive, and that will give us positive 24 millivolts. If we're working with a cation with a positive driving force, it will want to flow out of the cell. And then, just as a side note, an anion that has a positive driving force will want to go into the cell. So if we're working with chlorine or chloride that has a positive charge, it's going to want to go in. If it has a negative charge or negative driving force, it's going to want to flow out. Now I'm going to go switch gears and talk about action potentials and how they happen, specifically in neurons. So we can represent an action potential with a graph. This will represent time, and this will represent millivolts. And what's happening in an action potential, I'll explain in detail in just a moment, but essentially, because the cell's so negative, what's happening is it receives a signal to become more positive, and that positive is going to what's called depolarize the membrane. And I'll explain what specifically happens in an action potential. So we start here at negative 70 millivolts. And let's say we have a graph with these three numbers to represent our action potential. So the very first step of the action potential is we're at resting membrane potential at negative 70 millivolts. At this stage, potassium leak channels are open. And that is the only thing influencing the charge of the cell. As the action potential increases, we call this a graded potential, which means a cell is depolarizing or getting less negative, but is not quite reaching an action potential. That is influenced, if I label 1 and 2, that is influenced by mechanically and ligand gated sodium channels. Because sodium has a driving force of positive 54, it wants the cell to be more positive or less negative, if you will. And so those channels are beginning to open, which is allowing the cell to become more depolarized or become less negative. Once the charge reaches what's called threshold, which usually in a typical cell it is -55, that's where the cell gets so positive that's going to allow voltage-gated sodium channels to pop open. And when that happens, it's going to shoot up like that to positive 40, because that sodium now has a way to get in, and because it wants the cell to be more positive, the sodium is just going to rush through into the cell and cause the cell to be more positive, and that is how neurons receive a signal. And so they're going to pop open. At the same time, though, potassium voltage-gated channels are going to just slightly open, kind of like a creaking door open, very slowly. Open slowly. So they don't really have a huge influence on the cell yet. And we can represent that as stages 3 and 4. Now, when the cell reaches a peak at +40, eventually that cell is going to be so overwhelmed with positive charges that voltage-gated potassium channels will suddenly pop open, while voltage-gated sodium channels will become deactivated. So if I represented this like let's say the sodium channel like this, and we represented this as the lid and this as controlling the activation versus deactivation. This is what happens at step 1 and 2. At step 3 through 4, we have the lid popped open and we're allowing all that sodium to go in. But now at step 5, that channel is still going to stay open, but that ball and string are now going to block the opening way. And so that's what causes the voltage-gated sodium to deactivate. And that's going to cause what's known as repolarization, or a return to the resting membrane potential. And that is represented by steps 5 and 6. Now, once the cell reaches threshold again, you can say this is 5 and 6. This is going to be 7. Our sodium voltage-gated channels are going to be completely closed. So voltage-gated sodium closed, and our voltage-gated potassium will begin closing, since it has reached back to its threshold. And because potassium is still flowing in, it has a stronger driving force towards -94. So it's going to do what's called hyperpolarization at step 8. And that's when voltage-gated potassium channels will close. Once they are closed, that resting membrane potential is going to instantly be returned. So the cell is going to return to its normal state and be ready for another action potential. A couple of things. We have 2 different types of periods that we want to be aware of, meaning how it influences when an action potential can occur. We have what's called the absolute refractory period and the relative refractory period. The absolute refractory period is represented in the area where the cell is past its threshold and in the positive, where the cell is past its threshold, regardless if it's positive or not. But it is past the threshold, and in an absolute refractory period, by all means, the cell cannot reach, or the cell cannot stimulate another action potential, regardless of the strength of any stimulus to reach another action potential. The relative refractory period is represented in this area when the cell starts to repolarize past the threshold and go into hyperpolarization. And essentially, that is describing how a cell it is possible for a cell to have another action potential, but because it is very hyperpolarized past the resting membrane potential, it is going to have a harder time reaching an action potential, so it will require a stronger stimulus. Last but not least, I'm going to go over capacitance and length constant. So let's say this is our axon. So now we know that a cell is at resting membrane potential. It has a certain voltage or it has a certain number that represents its resting membrane potential. We also know that it sends signals down the axon. How does it do that though? Well, first we want to describe capacitance. And essentially capacitance is the ratio of the separation of charges, or positive and negative charges, outside and inside the cell over voltage, which is just how the charges are separated. So when we describe capacitance, let's say we've got so many positive and negative charges in this area and very few in this area. These hills represent a myelin sheath. Now, how is capacitance related to signals traveling across? We know that in action potentials, the signal has to travel from one charge to the next. But in a non-myelinated situation, that's going to take a really long time. Versus in a myelinated situation, if I can draw that a little bit better, we've got it going here, but then it's also jumping clear down here, covering more distance. So, in other words, a high capacitance, by rule of thumb, indicates a low signal or low potential. So in other words, the signal is not going to travel as far and as efficiently. But in a low capacitance situation, so we have less charges separated from each other on one side and the other, we actually have a higher signal or potential. And how this is related to signals traveling across, we call the length constant, which is represented by lambda, and that equals the square of Rm over Ri. What do these mean? Rm represents the resistance of the membrane. So in other words, when a cell or axon is myelinated, it is going to have an increased membrane resistance because it is basically insulating the axon from the outside world and separating those charges. Whereas the Ri represents the internal resistance. So in other words, when a signal is traveling across and it encounters a negatively charged protein, that's going to inhibit that signal. And so basically what length constant is describing is how far a signal can travel down the axon, or how efficiently the sphere of influence, or what in class we call the Blum, is going to influence this whole signal traveling. And because we know by definition myelin will have a more efficient signal, or myelinated axons will have a more efficient signal, they are going to have a higher length constant. So length constant is going to be much higher because our membrane resistance is going to be higher, and our internal resistance is going to be a lot lower. And that will wrap it up for my discussion on Essay 2 for Exam 1 of Bio 461. Thank you.